Okay, in dealing with solutions, an important thing to talk about is concentration, or how much stuff is dissolved in the solution. So in general terms, all right, generally speaking, solids dissolve more if you increase the temperature of the solvent. All right, so solid solutes will dissolve better if there's a higher temperature of the solvent. Okay. The rate at which solids dissolve increases when you increase the surface area, which is one reason why when we were dissolving, say, the calcium chloride or the sodium carbonate, you might have found it to go faster if you kind of crushed the chunks and made them into smaller bits. Okay. Gases can also be dissolved, but they kind of have opposite rules. Solubility of gases decrease with increases with temperature. So one way to kind of think about that is soda pop. All right? Warm soda is flat because it doesn't hold on to the carbonation as well. All right? Whereas cold soda is more bubbly and fizzy and tastes better because it's holding on to the carbonation better. Okay? And then another thing that can help with the solubility of gases if you are able to increase the pressure, which is then going to essentially kind of push the gas back into the liquid. Okay? So, just kind of in less paragraph form, solids dissolve best when they are heated, stirred, and ground into small particles. Okay? Much easier to dissolve powder than it is a big chunk. Then gases tend to dissolve best when the solution is cold and pressure is high. So something you might see in relation to this would be something like this, a solubility chart. All right. And then on here you can see the trends. You can read this as far as temperature. At 80 degrees, you would be able to dissolve approximately 52 grams of calcium chloride into water. Okay. Or at 40 degrees, you would be able to dissolve 65 grams of potassium nitrate. Okay. Can you tell which substance on here is a gas? So one of the trends with gases was that as temperature increases, solubility decreases. So cesium sulfate would be a gas. All right. So just things you can interpret from a chart. Mathematically, concentration is calculated by molarity. You've seen this before in labs when you see something saying like 2m hydrochloric acid or 0.2m copper sulfate. All right? So molarity, which is represented by capital M, is your ratio of moles of solute to liters of solution or solvent. Okay? So really it's moles per liter. And that equals molarity. All right? So some calculations with this. Very simple question would be, what is the molarity of a solution made from 3.5 moles of sodium chloride and a volume of 500 milliliters? All right? So to do this, you need moles over volume. One thing to keep in mind is your volume always needs to be in liters. Okay, so 500 milliliters divided by 1,000 milliliters per 1 liter gives you 0.5 liters. Okay? And then, technically it's 0.5000 because of your sig figs in this number, but 3.5 only has 2 sig figs. So in the end, when you do 3.5 divided by 0.5, your molarity is 7. Okay. Another fairly simple calculation you might run into is what is the molarity of a solution made from 450 grams of lead-4 iodide and 2.5 liters of water. Okay, so this one, the conversion, you have to go from grams to moles, because molarity will always be moles per volume. Okay, so in that case, you do 450 grams of lead iodide, divide it by the molar mass of lead iodide, and that gives you 0.63 moles. And if you divide that by 2.5 liters, your molarity is 0.25 m. Okay. The trickier calculations, though still simple, are when you have two solutions or one solution and you need to change its molarity. Now, something to keep in mind with these is that, generally speaking, you don't have the option of dilution is making it less concentrated, okay? So you can't make it less concentrated by adding solid. You have to, and you can't take it out, you have to make it less concentrated by increasing your volume, all right? So, something to keep in mind with dilution calculations is that your moles of solute don't change. Okay, the only thing we're changing is our volume and figuring out what volume of water to add or what volume of concentrated solution to add to get it to whatever we want it to be. Okay, so if you think of molarity as a calculation, all right, molarity equals moles over volume. And we're going to have two variations of this, because there's whatever we start with, and then whatever we want the new molarity to be. All right. Now for both of these, the moles don't change. That's going to be the same. We don't add any more sodium chloride or remove sodium chloride. We can only adjust volume. So if you write this, M1V1 equals mole, and that mole is also equal to M2V2, you can really think of these problems as your molarity and volume of your original solution has to be equal to your molarity and volume times the volume of your second solution. Okay? So again, keep in mind that your volumes must be in liters. Okay, so 50 milliliters is 0.050 liters. Okay, and 1,000 milliliters is 1 liter. So then to plug this in, this is V1, M1, and we know V2, we want to find the new concentration, M2. So that's going to be 0.40 times 0.0500 equals 1 liter times M2, your new molarity. So ultimately you end up dividing by 1. So your new solution molarity is going to be 0.4 times 0.05 or 0.2020 molar. Okay? Just some simple algebraic application of your molarity equation. So one more example of this. Again, it's another dilution sort of calculation, so you want to remember that M1, V1, so molarity, starting molarity times starting volume has to equal your ending molarity and your ending volume. So a chemist wants to make 500 milliliters of a 0.5 molar hydrochloric acid by diluting 6 molar hydrochloric acid. How much of that solution should he use? Okay, so if we make this our V1 0.5 liters, and our concentration is going to be 0.5 molar. All right, and then our M2 is starting out at 6 molar, and what we want to know is V2. All right, so do 0.050 molar times 0.5 liters equals 6 molar times V2. So we divide both sides by 6. You can even see that your molarity cancels out, leaving you with liters, which is what we want to find. 0.050 times 0.5 divided by 6. Okay, so V2 equals 0.004, and then based on all of our sig figs, we can keep one more. 42 liters, or in kind of more understandable terms, 4.2 milliliters. All right, so 4.2 milliliters of our 500 milliliter solution will have to be the 6 molar hydrochloric acid. The rest of it, so 500 minus 4.2, or 495.8 milliliters, would have to be just water. Okay? So make sure you do the online quiz, and I will see you in class.